Imagine a universe where speed bends time, starlight turns into a blue-white furnace, and dust grains hit like tiny bullets. Tonight, we chase the edge of the possible why light speed is the cosmic hard limit, and how near-light strategies flirt with that horizon without ever crossing it. From exploding energy budgets to shields that think from geometry that guards causality, to bodies that must outlast the glare, this is the truth behind the dream of ultimate velocity. If that journey sparks your curiosity, tap like subscribe and let us begin. He stands in a dim observatory and lets centuries of measurement assemble into a single hard horizon. The speed limit begins with timing. In the 17th century, an astronomer reads delays in the eclipses of Jupiter's moons and realizes that light takes time to cross space. 2 centuries later, experimenters send flashes between spinning mirrors, count teeth on wheels, and measure a speed near 300,000 kilometers per second. The number repeats across baselines and methods and refuses to yield to motion of the apparatus or the planet. That stubbornness becomes clue and boundary at once. The more the methods improve, the more the value remains fixed until the constancy itself demands a change in how the world is described. If the speed is the same for everyone who glides without acceleration, then the old rules for adding velocities cannot survive. A train's headlight and a lighthouse beam both ride a geometry that refuses to share their pace with the platforms that carry them. The insight is not an anecdote about light. It is the seed of a new structure. Space and time, once treated as separate stages upon which motion plays, must fuse into a single fabric, whose threads arrange themselves so that all observers agree on the speed of light in vacuum. Rulers shrink along the direction of motion, clocks tick at rates that depend on their state of motion, and simultaneity becomes a local agreement rather than a universal decree. These changes are not semantic. They are the only way different observers can reconcile their measurements while keeping the constant speed intact. He watches theory meet machinery. Atomic clocks fly on aircraft and sit atop mountains, and their rates shift by amounts that match the predictions. Moons born in the upper atmosphere live longer as they race downward than they would at rest because their time stretches with speed. Particle rings at the European Organization for Nuclear Research whip protons close to the limit, yet no amount of additional energy makes them touch the limit. The energy goes into mass energy and into the geometry of motion, not into pushing the particles through the ceiling. Each confirmation ties the limit to the world more tightly. None of it depends on belief. It depends on timing, on decay rates, on consistently repeated numbers. He looks outward and backward in time. Light from remote galaxies arrives stretched to the red not because it grew tired, but because the space it crossed expanded while it was in flight. The color shifts, the speed in vacuum does not. Gamma-ray bursts crackle across detectors in orbit and on the ground, and careful studies compare the arrival times of hard and soft photons that left together. If the vacuum hid a rule that made the speed depend on energy, billions of years would magnify tiny differences into measurable delays. Those delays fail to appear within the limits of the measurements. Even ripples in spacetime itself, the gravitational waves produced when massive objects collide, slosh across Earth at a pace that matches the light from their associated flashes within narrow bounds. The message holds from the smallest laboratories to the largest scales the sky can provide. Light is not special because it shines. It is special because it is the messenger that always moves at the maximum pace the fabric allows. He considers what the limit is and what it is not. It is not a counsel to go slow. Nothing in the rule prevents motion at a large fraction of the limit if energy and protection can be supplied. The band is narrower. No object with rest mass can be pushed across the ceiling in empty space. That restriction protects cause and effect. If a signal could run ahead of the light, then some observers would watch an effect appear before its cause. The world would tangle into contradictions. Instead, the geometry of space-time ensures that the signal cone that defines possible influence never opens wider than the constant speed. What looks like a forbidding law is in fact a promise that events will line up into stories that can be told without paradox. He senses the outline of the problem that the rest of the journey will explore. To approach the limit is to enter a world where everyday ideas fail in orderly ways. Ahead of a near light craft, starlight would swing to shorter wavelengths and intensify. Behind the sky would dim and redden. Interstellar dust grains, harmless at ordinary velocities, would strike with the energy of bullets. The clock on board would tick more slowly than clocks left on Earth, so that years for the crew might align with decades for those who watch the trajectory from home. The constant speed guarantees that a plan for a hard dash between stars must face more than distance. It must face the reshaping of time, the multiplication of energy demands, and the rise of hazards that appear only when motion acquires extreme pace. He turns once more to the instruments that anchor confidence in the rule. Maxwell's equations for electricity and magnetism already carry the speed within their form, and modern detectors such as the laser interferometer, gravitational wave. Observatory and partner observatories have witnessed ripples in space-time arrive alongside light from distant cataclysms, showing that even gravity's waves share the same cosmic pace within narrow bounds. Across scales from laboratory beams to galaxies, the message holds steady, and the horizon waits unchanged ahead. He ends this opening pass with the simple recognition. The constant speed is not merely a habit of light. It is a property of space-time. Light sits at the ceiling because it carries no rest mass. Everything that carries rest mass pays an ever-growing price as it accelerates. No laboratory has found an exception, not in particle beams, not in cosmic ray air showers, not in the timing of pulsars that sweep the sky with the lighthouse precision. The limit is the rule that lets the rest of physics keep order. It is not a wall that mocks ambition. It is the frame that turns ambition into coherent plans. Within that frame lies the task ahead to understand how engines, shields, bodies and minds behave as they approach the horizon, and to ask what strategies might dance along its edge without ever crossing it. The boundary stands. The intrigue grows where it must at the place where facts tighten and imagination begins to test them. He stands at the chalk edge of the problem and follows the price that motion demands as speed climbs. The first fee is paid not in coins but in energy. To push anything with rest mass closer to the constant speed of light in vacuum engines must pour in ever more energy for ever smaller gains in pace. The increase does not behave like a friendly curve that rises gently. It steepens until it becomes a cliff. Particle physicists do not talk about this cliff, they build against it. In vast rings, the European Organization for Nuclear Research sends protons chasing one another at a speed that is a breath beneath the limit, and the injected energy swells their kinetic stores and their effective resistance to further acceleration so fiercely that an additional surge of electricity lengthens their lives in the laboratory frame more than it increases their speed. The protons approach the horizon and discover that the horizon retreats with every step. This is not a trick of words. Time dilation defined once and now used plainly is a measurable stretching of time that unfolds as motion grows. Clocks carried by fast movers tick more slowly than clocks at rest, with respect to the observer. In the air showers of cosmic rays, muons that would normally decay in microseconds make it to ground because their motion stretches their time. The message holds for technology as well. The constellation of spacecraft that makes the global positioning system possible would be unusable unless engineers correct for both motion-based dilation and the slower pace of clocks deeper in the gravity well of Earth. These are not philosophical decorations. They are guardrails one must build into any serious attempt at speed. He turns from time to fuel and finds the same pressure. A rocket that carries its propellant must pay a compound price. The faster it wants to go, the more propellant it must lift at launch, and the more propellant it must then carry to accelerate that additional propellant. This compounding cost yields designs that balloon in mass to gain only incremental velocity. Chemical energy cannot pay the bill. The best chemical engines that fling probes across the solar system yield exhaust speeds of a few kilometers per second, and even staged and clever trajectories only steal extra speed from planetary gravity fields. Ion engines and plasma thrusters improve the efficiency by sipping propellant and pushing for months or years, yet their gentle thrusts cannot climb the sheer wall that rises near a large fraction of the limit. Nuclear thermal engines promise hotter exhaust and higher performance, but their gains, though real, are arithmetic gains. The underlying curve that demands an explosion of energy as speed nears the ceiling remains untouched. He lets two examples sharpen the contrast. The Parker Solar Probe dives deep into the gravity well of the Sun and reaches around 200 kilometers per second at perihelion, the fastest human object to date by a wide margin, yet that astonishing pace is less than 1,000th of the speed of light. The twin Voyagers streaming into interstellar space after gravity assists from giant planets travel at tens of kilometers per second, a noble drift on human scales and a crawl on cosmic ones. The gulf between impressive and adequate yawns wide because the ceiling is so high and the curve so steep. If the aim is even a tenth of the speed of light, the energy required for a ship of any meaningful mass becomes staggeringly large. He imagines a notional starship with a payload measured in tens of tons. To accelerate that craft to a tenth of the limit and then brake at the destination so that it can arrive intact requires energy comparable to the output of large power stations running for years, and that is before accounting for the heavy shielding redundancy and life support that a human mission would demand. The problem becomes still sharper when one includes the energy needed to push the propellant itself. Antimatter, which will have its own place in this journey, glows in prospect, because a gram of antimatter meeting a gram of matter releases energy on a scale that chemical bonds cannot dream of. Yet the production, storage and control of such fuel present barriers as formidable as the energy budget it promises to solve. He watches the geometry of motion ripple through every system aboard. As speed rises, the ship meets starlight as a hail of higher energy photons from ahead, a hazard to materials and to flesh that requires thick shielding or active fields to deflect or absorb. That shielding adds mass, which adds to the energy cost, which tightens the spiral. Waste heat that seems trivial at low speeds becomes a trap at high speeds, because radiating it away into space requires large radiators, and radiators add area and mass and vulnerability to impacts from interstellar dust, whose harmless grains transform into hypersonic projectiles at near light pace. Everything that protects also weighs, and everything that weighs asks for more protection. He extends the thought to time itself, and watches mission planning bend. To a crew rushing at a large fraction of the limit, months or a few years may pass on board, while decades pass for those who remain bound to Earth. Time dilation offers a bittersweet gift: shorter subjective travel times at the cost of losing synchrony with home. Communication windows shift, cultural ties stretch thin, and every plan must accept that the crew and mission control will live on different calendars. If machines go in place of humans, the time problem becomes an autonomy problem. A craft will have to decide, repair, and adapt without help that can reach it in real time. That autonomy in turn demands computation hardened against radiation and failure, which demands power and mass, which returns to the energy ledger. He returns to causality's quiet defense and feels how the physics polices the limit without malice. If more energy could always buy more speed in a linear way, then the temptation to cross the boundary would be an engineering dream away. Instead, the price curve steepens until it swallows plausible budgets whole. A metric of spacetime, not a bureaucrat, says no. The consolation is clarity. Every gain comes with a calculable cost. Experiments with particle beams, with high-altitude clocks, with deep space probes, and with astronomical timing, all align to show that the predictions of special relativity sit not in the clouds, but on the lab bench and in the sky. The mysteries ahead do not cancel these facts. They lean on them. He considers the hypothetical cheats and finds that each merely moves the payment to a different account. Beamed propulsion that uses lasers to push a sail frees the craft from carrying propellant, but burdens the beam source with staggering power and perfect aiming across light years. A magnetic scoop that harvests interstellar hydrogen as reaction mass inherits the thinness of that medium and the drag that gathering it would impose. Fusion pulses promise high exhaust velocity, but the hardware to stage and focus those pulses must survive a storm of its own making, and then must face the same time and hazard regime as any fast traveller. Even warp analogies that speak of bending spacetime instead of moving through it demand exotic energy densities that current physics does not know how to assemble in practice, and they make promises that would still have to square with causality's guard. The conclusion of this stage is not a defeat, but a frame. The price tag for near-light travel is stitched into the way space and time share their structure. Where speed rises, energy cost rises faster. Time stretches, hazards harden, and architecture complicates. Ambition can live here, but only as design that respects the curve. The next steps will probe the consequences more closely from cause and effect to the interstellar medium that turns from whisper to weapon, and from there into drives that try to tame the bill without breaking the rules. He moves to the boundary where sequence itself begins to wobble and asks what the speed limit protects. Causality is the simple rule that causes precede effects in every valid description of an event. In the geometry of spacetime built by special relativity, that rule appears as a light cone around every event. The interior of the forward cone holds all the places that can be reached by signals that respect the constant speed. The interior of the backward cone holds all the places that could have sent a lawful influence. Outside both cones lie regions that are out of causal reach. If a signal were to travel faster than light in vacuum, that signal would leap outside the cone and become space-like, and then different observers sliding past one another at lawful sublight speeds would disagree on the order of cause and effect. In some perspectives, the effect would appear to happen before the cause. The story would not merely be confusing, it would be contradictory. The same geometry that forces rulers to shrink and clocks to stretch also keeps the arrow of events from curling into knots. He follows a clean thought experiment. A beacon on a ship sends a pulse that outruns light to a receiver on a station. In one frame, the ship sends first and the station receives later. In another lawful frame moving at a high but sublight speed relative to the first, the reception can be computed to happen before the emission. If the station could then send a reply by the same faster-than-light channel back to the ship, a cycle would close in which the ship receives a message before it decides to send the original pulse. The paradox is not a philosopher's toy. It is a geometric prediction if such channels exist. General relativity, which allows spacetime itself to curve, adds further caution. In certain solutions to the equations, curves exist that loop back on themselves in time. These are called closed time-like curves, and they are paths along which a traveller could, in principle, revisit an earlier event in his own history. The mathematics permits such structures under special and often extreme conditions, but the physics resists them. Energies and stresses required to hold such loops open appear to demand exotic negative energy densities not known to exist in stable, macroscopic form. The physicist Stephen Hawking summarized that resistance as a chronology protection conjecture, the idea that the laws prevent macroscopic violations of causality. The conjecture is not a theorem, but it expresses the way theory and experiment have conspired to deny any laboratory path to time disorder. He checks quantum theory where entanglement often wears the costume of instant action, and finds another guard. Entanglement links the outcomes of measurements on separated systems, but it does not carry useful information faster than light. The statistics that any one observer can read from his local measurements are unchanged by choices made at a distance. Only when the observers later compare their records at speeds no faster than light do the correlations appear. This no signaling rule in quantum theory does not arise from politeness. It arises from the math that preserves causality inside a probabilistic world. Experimental tests have tightened the bounds closing loopholes that once left room for hidden channels, and yet the rule stands. The safety of sequence is woven through both pillars of modern physics. He considers a common confusion that tries to sneak past the guard by pointing to faster-than-light phenomena that already exist in media. Cherenkov radiation flashes when a particle crosses water or glass, faster than light moves in that medium, and phase fronts in some waveguides can move faster than the vacuum speed. Neither breaks causality because neither transports information or energy faster than light in vacuum. The true ceiling is the vacuum limit, and every attempt to smuggle a signal across it finds its content dissolved or delayed until the guard has been satisfied. He turns back to near-light travel and asks what happens at the edge where causality bends but does not break. Relativity of simultaneity, defined once and used plainly now, is the rule that different observers moving at different lawful speeds need not agree on which distant events are simultaneous. The faster the relative motion, the more the plane of now tilts. At ordinary speeds, the tilt is undetectable. At near light speeds, the tilt changes how a traveller slices the universe into before and after across great distances. This is not a loophole in cause and effect. It is the way the geometry keeps order while allowing different observers to write different but consistent narratives. He lets the twin thought experiment so often used do its quiet work but strips it of drama. One twin stays on Earth. One twin rides a high-speed loop and returns. The traveller ages less because his path through space-time is different and includes accelerations that break the symmetry. There is no contradiction because the world line of the traveller carries a different proper time, the time measured on his own clock. The conclusion is not that time travel has occurred, but that time is not a universal river. It is a dimension that can be traversed along different tracks, all of which keep the order of causes and effects intact. He revisits the empirical anchors, the laser interferometer. Gravitational Wave Observatory and its partners have measured space-time ripples from colliding compact objects and compared their arrival with light and gamma rays from the same cataclysms. Within tight limits, both arrive together, suggesting that gravity's waves and light share the same cosmic pace. High-energy photon studies from distant explosions look for dispersion, a sign that different energies move at different speeds through vacuum. Within the sensitivity of the data, such dispersion does not appear. Past anomalies that seem to hint at faster-than-light particles have fallen to careful remeasurement that found mundane errors in cables and clocks. The line holds not because the community wishes it to hold, but because instruments and cross-checks keep pointing to the same ceiling. He lets speculation enter, but only with caution. If spacetime could be engineered to move rather than the ship as in the family of ideas called warp metrics, then perhaps the craft would remain locally at rest, while the space behind expands and the space ahead contracts. In such constructs, the craft would never outrun light in its local patch, so causality would not be directly violated. Yet even in the friendliest versions, the edges of such a bubble threaten to create horizons that sever communication with the outside world, and to enable closed time-like curves when manipulated in certain ways. Energy conditions that forbid negative energy densities must be bent or broken to hold the geometry in the desired shape. Quantum effects that allow tiny negative energy densities for brief moments appear to place strict limits on how such exotic matter can be arranged. The horizon of possibility remains far, and the guards of chronology still stand watch. He finishes this pass with a recognition that ties the future sections to a necessary discipline. Near-light strategies must coexist with causality. Beamed sails may lean on light to push without carrying propellant, but the beam must still travel at or below the limit and must be aimed and modulated with the delay that the distance imposes. Fusion pulses may throw exhaust at a significant fraction of the limit, but they will not send a signal ahead of the light cone. Autonomous craft may anticipate and adapt, but their decisions will unfold along world lines that never cross forbidden regions. The edge of causality is not a cliff to leap from. It is a rail to hold while climbing toward extreme speed. The mysteries that remain are many, and will deepen as the hazards of the interstellar medium and the ferocity of radiation at speed enter the frame. The guard that maintains order does not deny ambition. It demands that plans be drawn with cones and clocks as rulers, and that every tempting shortcut be measured against the oldest promise in physics, which is that effects do not outrun their causes. He turns his attention from laws to landscape and finds that the thin material between stars becomes a gauntlet when speed grows. The interstellar medium, which reads like emptiness at human pace, is a tenuous blend of gas and dust shaped by old supernovae and the winds of young stars. In a cubic centimetre of this space there may be a fraction of a particle to a few particles, and yet at a large fraction of light speed each particle matters. Hydrogen atoms become hammer blows, helium and heavier ions bite harder, dust grains most smaller than a hair, and many as tiny as a smoke mote harden into projectiles that strike with energies that defy intuition. He anchors the picture with the neighbourhood that probes have already touched. The voyagers crossed the heliopause, the boundary, where the breath of the sun yields to the ambient medium, and felt the change in particle populations. The interstellar boundary explorer mapped a sky of energetic neutral atoms that traced the interaction between the solar wind and interstellar gas, a faint ring that sketched the pressure of the outside environment. New Horizons carries dust detectors that count the drifts and peaks of tiny impacts all the way past Pluto and into the distant Kuiper belt. The data agree on a paradox that matters for travel emptiness is not empty enough to ignore. A ship that sprints has to treat this whisper like weather that can wreck. He examines impacts first because mechanics cares little for philosophy. A grain that weighs less than a microgram at rest behaves like a bullet when the relative speed becomes a tenth of light speed. Its kinetic energy turns to heat and shock upon contact. Whipple shields, which use a thin sacrificial layer to shatter an incoming particle before it reaches the main hull, protect satellites and stations from orbital grit that arrives at a few kilometers per second. At tens of thousands of kilometers per second, the same concept faces new physics. The initial vapor cloud becomes a plasma blowtorch that spreads sideways and digs into the layers behind. Multiple spaced plates, foams, or aerogel stacks can lengthen the path over which the energy spreads, but each layer adds mass, and mass multiplies the energy bill that Section 2 has already tallied. Magnetic fields offer hope against charged particles, but dust grains are often neutral and only partly ionize in the bow shock. Electric fields can in principle charge and deflect grains, but the fields must reach over distances that scale with grain size and speed, and at extreme pace the grain becomes a coherent projectile until it is very near the shield. He imagines a bow facing the wind, a forward structure that accepts ruin so that the vessel behind can live. Such a shield might be replenished in flight by ablating fresh surfaces, or it might be carried like a detachable barge and dropped after it has served to slow the craft at the destination. That notion leads to an architectural loop. The shield is heavy in front, so it increases the load that needs shielding. The design becomes a negotiation with cascading penalties. He adds gas to the picture and finds heat. Hydrogen atoms drifting at thermal speeds enter the path of the ship, and in the ship's rest frame strike at enormous energies. Each collision knocks electrons free, lights the bow with a shock sheath, and generates radiation that bleeds along the flanks. At high enough speeds, the blue shift of the background light of the universe and of the starlight ahead fills the forward sky with higher energy photons, and the gas that feeds the bull shock glows. That radiation hazard belongs formally to the next section, but here it rises as a secondary effect of a mechanical problem. The bow that must take dust must also take a bath of light and particles that bake materials and electronics over time. The craft must carry not just a nose that resists punch and grind, but a skin that survives long-term erosion and embrittlement. Microcracks that a builder can ignore at low speed become paths for catastrophic failure when a grain opens them at a tilt and the stress field finds them. He remembers a quiet experiment that hints at scaling. The Stardust mission captured comet dust in aerogel at speeds of several kilometers per second and brought the tracks home a feathered series of tunnels where grains entered shocked and slowed. Those tracks are graceful at that pace. At near light speed there is no gentle tunnel. There is a burst of plasma that moves at shock speeds within the shield material, and a fan of ejector that can spray the hull behind. Choices of material become fraught. Metals conduct heat and electricity but can spall and crack. Ceramics resist heat but can be brittle. Composites offer strength to weight but must be understood grain by grain for how they respond to ultra-fast, ultra-small punches. He watches concepts multiply in the literature. A forward dust cloud could be projected by the ship itself, a mist of sacrificial particles that collide with incoming grains at a distance and shatter them into a more manageable hail. A plasma magnet, a device that inflates a magnetic bubble with a little injected plasma to create a large standoff shield, might hold off the charged component of the flow and shape the bow shock to deflect plasma around the craft. A combination of patterns might be best: a physical bumper for the largest grains, an electromagnetic sheath for ions and electrons, and fine dust projected ahead as a sacrificial screen. Each of these needs power control and mass, and each must survive without constant human maintenance, because the distances will erase real-time support. He steps back to a grander scale that matters for route planning. The neighbourhood of the Sun sits within the local interstellar cloud, a patchwork of warmer and cooler regions, denser and thinner streams, all set within a larger local bubble, carved by ancient explosions. A traveller cannot assume uniformity. There are knots of dust along some lines of sight and clearer windows along others. Astronomers map extinction, the dimming of starlight by dust, to trace these structures. A starship design that accepts impacts within a certain flux may find room for higher speed along a carefully chosen corridor, and may have to slow for a murkier lane. The medium is a weather map written over light years, and a craft that moves fast enough makes that weather matter in a day-to-day way. He remembers the temptation to harvest mass from the medium, a dream that arrived with the idea of a magnetic scoop that gathers hydrogen ahead and burns it to generate thrust. In stillness, this seems elegant. In motion, the scoop becomes a drag device because shaping magnetic fields to capture incoming protons slows the craft in the process of collection. And the thinness of the medium means that the power gained often loses to the power lost, unless speeds and field strengths fall into a rare balance. The idea does not die, but it does shift from engine to brake. A magnetic sail can in principle shed speed by pushing against the ambient plasma of the medium near the destination. The interstellar medium, dangerous at the bow on the way out, becomes a partner in stopping when the aim is to come to rest. He lets the meaning settle. The medium dictates architecture. A forward shield, a protective electromagnetic geometry, sacrificial material stores radiators that are shadowed behind the shield, and sensors that watch the forward flow and adjust in real time become baseline rather than exotic. Every gram saved in the shield increases the odds of reaching a target speed, and every layer removed increases risk from a rare large grain. Statistical arguments rule design. Over a path of many light years, the chance of encountering a particular grain size distribution multiplies until events that are unlikely per meter become likely over the journey. Redundancy and modularity become virtues. A forward module might be designed to be swapped out after a large hit. A wing of radiators might be folded behind a shadow during heavy flux, and the ship might carry the ability to lay down its own debris field temporarily to create a clearing. He closes this survey of space between stars with a simple, sober taste. The emptiness that allows light to cross with little attenuation becomes a storm when the vehicle moves at near light pace. The very speed that makes a mission plausible turns the medium into a weapon that must be predicted, watched, and tamed without pause. The next steps will look at the radiation regime that rides with this mechanical hazard, because particles and photons, once shifted by motion, carve paths through matter and through biology that demand still more armor and still more care. Speed is not only about engines, it is about the thin fog that becomes shrapnel and the soft glow that becomes a furnace when the ship leans too hard into the night. He turns to the glow that bathes the universe and finds it sharpening into a blade when speed mounts. Radiation begins with a simple shift of color and ends in a complex storm of particles and photons that carve through matter. As a craft moves at a large fraction of the speed of a light, every photon ahead carries more energy in the craft's rest frame. Starlight that would warm a dark deck slides toward ultraviolet, then toward X-rays, and for still higher pace toward gamma rays that split chemical bonds and seed cascades in metal and in flesh. The soft shimmer of dust lanes becomes a harsh headlight. Behind the sky fades and reddens, but the bow inherits a cone of intensified glare, a forward hemisphere where the spectrum hardens, and where any exposure accumulates into dose. He watches matter join the light. The interstellar gas that Section 4 counted as mechanical shrapnel also becomes a radiation source. Incoming hydrogen and helium stripped and shocked at the bow light a sheath whose photons travel along the hull. Electrons torn loose by collisions spiral in whatever magnetic fields the craft carries, for shielding or for power, and their turns produce radiation akin to synchrotron light. This glow may not be born in laboratory rings, yet its character is familiar higher energy, when curves are tight and when particles are swift. In the same way, electrons breaking in dense material throw off Bremsstrahlung, a fan of hard photons that can pierce where the original charged particle would have stopped. A hull designed only for mechanics can become a light source that feeds on its own protection, and so materials and geometry must be chosen to absorb without brightening the very hazards they seek to soften. He lets specific skies illustrate the risk. The cosmic microwave background, a bath at a few Kelvin in the frame of the stars, looks harmless when a traveller rests. At modest fractions of the speed of light it warms and brightens in the forward view. At still higher fractions, the forward patch of that background turns from long waves into short waves, and the gentle sea becomes a faint drizzle of more energetic photons. Meanwhile, starlight and the glow of dust in the galactic plane are blue, shifted more dramatically, and arrive from a narrowed cone because of beaming, so that energy that once streamed from half the sky is squeezed into a smaller window with greater intensity. A ship that wishes to sprint must treat the forward sky as a furnace door that refuses to close. He remembers the past work that taught caution. Astronauts have watched flashes behind closed eyelids as cosmic rays cross eyes and trigger light in the retina. Instruments flown on high-altitude aircraft, on balloons and on satellites have logged the relentless drizzle of protons and heavier nuclei from space, and storms tied to solar eruptions have forced shelters in orbit. These are slow environments by design, yet even here the dose accumulates. At near light pace, the fluxes and energies spike in the bow frame, and what would be a minor concern across years becomes a hard limit across months. Particle showers born in shielding create secondaries, including neutrons that are hard to stop and that lodge their damage deep. Single energetic ions slice through DNA and leave double-strand breaks that a cell struggles to repair, and clusters of such breaks in a tight volume can defeat biology's careful machines. He considers the first line of defense and finds that no single layer suffices. Dense metal stops charged particles well, but breeds Bremsstrahlung and secondary neutrons under ion strike. Plastic rich in hydrogen slows protons and moderates neutrons, turning fast trouble into slow capture that can then be soaked by a follow-up layer. Water essential for life doubles as a shield and as a heat sink. Fuel and waste can be arranged as sacrificial mass around crew spaces. Magnetic fields can sweep away charged particles before they strike, yet those same fields bend electrons into tight turns and raise the risk of synchrotron light, unless field shapes and strengths are chosen with care. An electromagnetic cocoon that inflates a magnetic bubble with a small plasma may hold off a portion of the flow at large standoff, but the power to maintain it and the dynamics of the bow shock demand constant attention. He looks at heat, the quiet partner of radiation. Every photon absorbed adds to thermal load, and every particle that stops shares its energy as heat. At near light pace, the bow is a continual heater, and the craft must throw that heat away through radiators. Those radiators must hide behind the shadow of the shield, or be angled to stare only at the dark aft sky, else they will face the same blue shifted glare they are trying to reject. Emissive panels that would suffice for a slow probe must grow in area, and must be segmented and armoured or folded and tucked, when a heavy dust lane or bright star field looms ahead. Cooling loops become part of survival, not convenience, and any leak in a piping run is not a maintenance ticket but a hazard that may bloom into failure when the heat has nowhere to go. He compares machine and body, and sees a narrow passage. Electronics suffer single event upsets, as lone ions flip memory states and trigger false commands, so logic must vote, must check, and must restart without complaint. Sensors must peer through glare and report accurately when the view changes with speed, and that means continuous calibration under a moving spectrum. Human tissue absorbs dose unevenly and ages under it, so storm shelters at the center of mass thick with water and plastic become a core feature. Crew routines must include time in that shelter during passages through bright forward glare or when crossing regions with known high dust or gas density. If hibernation someday proves safe, it would serve dose economy as well as psychology, because narrow, well-shielded pods are easier to protect than a broad living volume. He lets braking enter the frame because speed is not only a beginning. A beamed sail pushed by light must turn and face the beam to stop, and that turn reorients the glare. A fusion drive that throws exhaust must plan a long glide and a gentle burn that keeps the bow within a survivable dose. A magnetic sail that pushes against plasma near the destination can slow a probe without a heavy propellant reserve, but it must inflate its fields in a medium that itself grows brighter in the craft frame as speed remains high. In every case, the dose ledger forces choreography as strict as the energy ledger. He opens space for speculation, but only after the anchors are set. Perhaps a forward plasma cloud renewed continuously by a small generator could both prionize dust and scatter light, dimming the hardest photons before they reach the primary shield. Perhaps thin layers of novel metamaterials could reflect selected high-energy bands away from critical structures, although ordinary materials do not reflect X-rays and gamma rays, and must instead absorb or scatter them. Perhaps a wake of tiny drones could fly ahead by a tiny margin and project a sacrificial fog that catches grains and seeds, a luminous bumper at a distance. Each idea drags power needs control loops and maintenance realities behind it. He ends this pass with a clear pattern. Radiation at near light speed is not an accessory to the problem. It is the air that a fast ship breathes. Blue shift concentrates danger ahead. Particle strikes breed secondary photons and neutrons that penetrate and linger. Shielding must be layered, shaped, and lived with, not merely installed. Heat must be treated as failure if it cannot escape. Biology and electronics must be assumed vulnerable, and therefore must be designed to err gracefully and recover often. The promise of speed carries a permanent invoice that must be paid in mass, in power, in habit, and in time. The next step turns from the general sky to nearby laboratories, because the solar system already offers a set of proving grounds, where materials, fields, and flight plans can be pushed against this storm before a true sprint across the dark is attempted, and those trials will reveal which protections are dreams and which are tools. He looks inward for rehearsal space and finds that the solar system is a gymnasium full of ramps, furnaces, and particle storms where near-light ambitions can be tested without crossing the abyss between stars. The inner system hosts the most punishing heat and glare that any fast craft will face, so missions that graze the sun become laboratories for materials and for flight through blue, shifted light. The Parker Solar Probe already dives closer to the Sun than any prior craft curling through perihelion at speeds of hundreds of kilometers per second and enduring a radiative bath that drives its carbon composite shield to temperatures that would ruin ordinary metals. Its survival teaches one lesson in geometry: hide delicate systems behind a fixed shadow, and make that shadow reliable through control that never sleeps. The European Space Agency Solar Orbiter adds tenacity by bringing telescopes and instruments into that same harsh regime, showing how sensors must see through glare while their housings hold a steady thermal plateau. Together, these craft show how radiators must stare into the dark and how coolant loops must shunt heat to regions spared the fiercest light, and they reveal how even subtle contamination will bake into mirrors and lenses if not prevented. He turns to the gas giant Jupiter, because it offers the closest thing to a particle accelerator in the sky, a beltway of radiation that can cook electronics at ranges where sunlight is gentle. The Juno spacecraft loops through that environment and survives by building fortresses around its logic and by shaping flight paths that tackle storms in short chosen bursts. There is a grim elegance in using the worst planetary radiation laboratory to prove how hardened computers can vote on their own sanity, rewrite their memory after single ion flips, and continue a mission without a human hand upon them. Any near-light craft will face a forward cone of radiation that is worse in many ways than the Jovian belts, so designs that thrive at Jupiter are not a luxury, but a rehearsal for the core problem. He visits the boundary where the sun stops and the interstellar medium begins, because that is the seam any fast traveller must pass. The twin Voyagers have stepped beyond the heliopause and continue to report the shift from a solar wind-dominated plasma to the ambient gas of the galaxy. Their plodding pace keeps hazards low, yet the long passage marches through the very structures that a sprinter will traverse in months instead of decades. Measurements of dust-neutral atom flux and magnetic field direction gained at this boundary help map where a future craft will find quieter lanes and where it will find knots and walls. The Interstellar Boundary Explorer paints a global picture from inside the heliosphere by catching energetic neutral atoms that result when hot charged particles in the boundary regions trade charge with cold neutrals. That picture lets designers draw not just a target star on a chart, but a planned path through pressure ridges and calmer seas. He gathers smaller laboratories into the frame. The New Horizons mission has carried a dust counter into the Kuiper Belt and beyond, reading a background of tiny impactors that informs how heavy a forward shield must be. The Dawn mission at Vesta and Ceres and the Rosetta mission at Comet Churyumov-Gerasimenko have flown through dust environments that forced careful modes of operation, including slewing to protect radiators and instrument faces, and accepting periods of safe configuration while grit thickened. The Lunar Reconnaissance Orbiter and other craft around the Moon have taught how regolith dust sticks and abrades, and how to design seals and joints that work despite cutting grit. These lessons stack up into an understanding that a fast ship must be a creature that always knows where its vulnerable faces are pointed and that can change posture with minimal wear. He lets timing instruments take the stage because a ship near light pace must know its position and velocity with exquisite care when small errors grow quickly into large misses. The global positioning system proved that timing in orbit must account for time dilation and gravitational potential, and the corrections built into that network show how unavoidable relativity is in practice. The Deep Space Atomic Clock, a demonstration flown by the National Aeronautics and Space Administration, showed that long-lived stable timing can be carried on a spacecraft, reducing reliance on two-way communication that would be too slow for a racing vehicle. Optical lattice clocks now reach stabilities that promise navigation by comparing timing against pulsar beacons, and radio astronomers have already used millisecond pulses as cosmic lighthouses to triangulate positions in the outer solar system. Any ship that runs fast will want clocks that do not drift, and will want sky references that do not fail when the forward view becomes a narrowed blue shifted cone. He turns to propulsion rehearsals that the inner system allows. Solar sails have flown pushed gently by light pressure, and while their accelerations are small, they teach the choreography of beam-pointing attitude control without propellant, and the delicate dance of keeping a thin film intact. A beamed sail concept can be trialled at smaller scales within the solar system, with ground or orbital lasers driving small probes to high but sub-relativistic speeds along long baselines. Such tests would reveal how a beam blooms in atmosphere, how it scintillates in turbulence, how adaptive optics must work, and how to hand off between beaming stations as Earth rotates. Ion engines and plasma thrusters have proven their longevity on missions like Deep Space One and Dawn, burning for years with steady thrust. Their plumbing grids and erosion teach how to manage a high-voltage machine in vacuum without failures that will be catastrophic when repair is impossible. Nuclear thermal propulsion, a legacy from the nuclear engine for rocket vehicle application era, is again under study for Mars-class missions, and while it will not break the near-light barrier, it can teach the materials and safety discipline needed for hot reactors in space and for high-temperature exhaust handling. He places human bodies within these testbeds because biology is not an accessory. The International Space Station has revealed how bone and muscle change without gravity, how sleep and mood shift, and how human systems deal with routine radiation doses. Missions beyond the geomagnetic shield, such as long loops around the Moon, and possible future stays on the lunar surface, will expose crews to higher doses more like deep space. Storm shelters, water walls, and plastics loaded with hydrogen can be trialled in real missions with dosimeters sewn into walls and worn on skin. The far side of the Moon, shielded from Earth's radio noise, is a natural site to test deep space communication and to stage long baseline interferometers that can also serve as navigation aids for probes heading outward. Long-duration autonomy can be practiced by setting spacecraft on tasks that demand self-repair and self-calibration. He returns to the unfriendly truth that the solar system also offers consequences for failure that are less final than interstellar flight. A shield tile can be swapped on a low Earth orbit laboratory. A reaction wheel can be replaced on a servicing mission. A radiation vault design can be revised after a Jupiter pass and flown again. Even with these mercies, budgets and schedules are not infinite, and every experiment must be designed to extract many lessons at once. So a test sail should include a fraction of a degree beam tracking experiment and a rat's nest of sensors to read how a thin film wrinkles under micrometeoroid pings. A sundiver should not only survive heat, but should carry a panel coated with candidate metamaterials and rotated in and out of the shadow to see which coating survives glare and dust. A navigation mission should carry both a traditional star tracker and a pulsar timing unit, and should log how each performs when the sun is nearby, or when the craft's own plasma plume contaminates the view. He lets a single architectural concept tie the testbeds back to the dream. A modular interstellar probe can be assembled in Earth-Moon space where heavy shields and radiators can be added, where power and beaming experiments can be done, and where tethered drones can practice flying ahead of a surrogate bow at high closing speeds. The probe can then sprint sunward fall toward a close perihelion and fire a high-impulse stage at the deepest point in the gravity well to maximize exit speed. That route imitates the dynamics of a true near-light launch in miniature and tests thermal and control systems in the right order. Past attempts at solar thermal stages and electric sails hint at an ecosystem of tools that can be mixed. The point of the inner system is not to pretend to reach the limit. It is to strip away surprises before surprise becomes fatal. When he gathers these lessons, a design philosophy emerges. Build shadows that do not fail. Harden logic and trust it to vote. Place radiators in permanent night. Use the worst natural laboratories to qualify for the worst artificial ones. Lean on precise time and on celestial beacons. Accept that any path to near-light speed must be paved with dozens of missions that look mundane until their data are inserted into a shape that can run fast. The solar system is a wind tunnel for the cosmic highway. A ship that cannot thrive here is not ready to face the narrowed blazing cone of the forward sky between the stars. He turns to engines and discovers that arithmetic rules ambition long before exotica enters the scene. Momentum must be thrown away to go forward, and every way of throwing it demands a price in mass power, complexity, or time. Chemical combustion stands first because it built the road to orbit and the early excursions beyond. Its energy lives in chemical bonds that, however refine the mixture, deliver only a modest push per unit mass. Exhaust rushes from a bell at a speed measured in a few kilometers per second, which is generous for launching from Earth yet meager for chasing the ceiling. Staging helps by discarding empty tanks. Gravity assists, help by borrowing motion from planets, and sun-skimming dives, help by firing at the bottom of a well. But the core figures remain stubborn. Chemical fire cannot hurl a meaningful payload to a large fraction of light speed without ballooning into a mountain of propellant that eats the mission before it begins. He shifts to electric thrusters that trade force for patience. Ion engines and plasma devices accelerate a sparse spray of atoms to far higher exhaust speeds than flame can provide. They sip propellant and push for months or years with exquisite control as missions that orbited distant minor worlds and threaded the asteroid belt have shown. Yet their elegance hides a quiet wall. To fling exhaust faster, they must accept high voltages and large power means heavy power sources and heavier radiators. The thrust they offer is gentle by design, and while that gentleness is perfect for climbing out of planets and spiraling between targets, it cannot by itself sprint toward 1/10 of the speed of light, unless the ship becomes mostly power plant and radiator array. He lets nuclear heat step onto the stage because fission can boil propellant to temperatures that chemical flame cannot survive. A nuclear thermal engine replaces the combustion chamber with a reactor core and runs hydrogen through it until the gas roars from the nozzle with far higher energy per kilogram than any chemical mix can give. Ground tests from an earlier era show that the gain is real. It promises brisker trips to Mars and swifter loops through the outer system. Yet even here the push is arithmetic rather than transformative. Exhaust speeds improve by factors not orders, and the mass of the reactor the shadow shields to protect the crew, and the radiators to dump heat, all eat into the margin. The design remains yoked to the same truth that every kilogram of protection and plumbing is a kilogram that must be accelerated and later slowed. He visits fusion because it tempts with star-grade energy. Concepts abound that squeeze plasma with magnets, crush pellets into tiny suns, or throw pulsed packets of hot gas from a magnetic mirror to make thrust. A ship that rides the blast of controlled fusion could in principle cast exhaust at a significant fraction of light speed, and thus need less propellant for the same gain and velocity. In practice, the physics demands choreography that has not yet been achieved outside vast laboratories, fuels that ignite readily confinement, that does not unravel repetition, that does not shake the machine apart, and conversion of furious heat and charged products into a directed plume without melting the nozzle or poisoning the structure. Even if compact fusion ignites, the engine will still feed a familiar pair of tyrannies: heat that must be expelled and radiation that must be stopped, and both tyrannies add mass. He considers the dream of fission fragments that escape a reactor at high speed and become exhaust, a route that tries to avoid wasting energy on heating heavy propellant. Physics allows fragments to depart at impressive velocities, but a reactor that both sustains fission and lets fragments leave in a directed stream is a puzzle of materials and geometry. Reactors prefer to keep their products to maintain the chain reaction. Hardware that lets those products go must survive radiation, maintain structural integrity under thermal stress, and shape the stream into a plume that does not sandblast the ship. As the materials grow exotic, so do the uncertainties about lifetime and serviceability far from help. He brings beamed propulsion to the table because it moves the power source off the ship. A sail shines under a laser or a microwave beam, and rides radiation pressure without carrying propellant, so the craft itself can be thin and light. Robotic scouts measured in grams to kilograms could in principle be pushed to a visible fraction of light speed if vast arrays pour their power into a narrow beam and hold it on target across millions or billions of kilometers. The ledger shifts, but it does not vanish. Diffraction spreads a beam. Unless the aperture is huge, the atmosphere boils the path unless stations sit in space, and the wonder of optics over long baselines demands correction, so precise that mist light becomes wasted energy. The sail must live through violent acceleration, keep its shape survive, dust hits, without tearing into a fatal run, and flip or reef for braking without a hand aboard. If the payload is heavy or human, the power required for beaming climbs into scales that demand infrastructure as large as cities. He returns to staged architectures because arrangement can harvest gains that raw engine performance cannot. Disposable stages fall away to shed dead mass. Tethers can spin and fling payloads like slings. Close dives near the sun can amplify finite thrust by firing at the bottom of the deepest local well. Depots in Earth-Moon space can let many small launches assemble a large ship over time. Each of these softens part of the bill, but none redraws the curve that steepens as speed rises. Arithmetic keeps its hand on the tiller, reminding designers that cleverness in choreography cannot abolish the rising price of approaching the limit. He weighs the tyranny of heat again because propulsion is also a thermal problem. High power makes hot components demand radiators demand area, and area invites impacts. Armor for radiators adds mass which demands more power and creates more heat. The loop tightens until it dictates architecture. Exotic liquid droplet radiators that spray curtains of coolant and recollect them with electromagnetic fields promise high performance, but raise new worries about dust strikes and control in a forward gale. Solid panel radiators can hide in the ship's shadow and stare only at the cold aft sky, but hiding limits their area and throttles power. No engine escapes that balance. He gives a nod to mass drivers that buy momentum by throwing pellets. A rail or coil device could spit tiny slugs rearward at breathtaking speed and yield efficient thrust while sipping propellant. In practice, a launcher that can accelerate a river of pellets for years, aim them perfectly and avoid fouling itself is a demanding companion. The mirrored idea of catching pellets from a distant beaming station to brake on approach invites its own edge case failures, because a single miss at near light pace is not a glitch but a weapon. He imagines hybrids that braid strengths. A probe could dive sunward for a gravity slingshot fire. A compact nuclear thermal stage at perihelion unfurl a sail to sip momentum from a beaming array for months, and finally spread a magnetic sail to push against the destination wind and shed speed without propellant. Such choreography spreads the burden yet multiplies the parts that must work without repair. Hinges, films, coils, reactors, optics, and clocks must all hold together while the forward sky brightens to a hard blue glare. He steps back and reads the pattern. Engines that exist today carry probes and people around the solar system with grace and patience. Engines that might approach a tenth of light speed dwell on paper, and in laboratories behind gates marked with words like materials, power, and heat. Closing the distance to the ceiling demands not a single revelation, but a braid of them dense and reliable power without crushing mass thrusters that turn that power into directed exhaust, without eating themselves radiators that throw heat, while hiding from the forward furnace shields that live under constant sandblasting and guidance that keeps the plume straight while the ship trembles. He ends this pass with a sober comfort. The arithmetic is harsh, but it is not mysterious, and that is a gift. It says what mass a tank must hold, what temperature a nozzle must survive, what power a beaming station must deliver, how far a radiator must glow, and how much margin a shield must carry. The figures turn dreams into engineering targets. The next steps move from engines that exist and engines that might toward architectures that let light itself become a lever, because if the ship cannot carry what it needs, perhaps the cosmos can push from afar, and perhaps staging can extend beyond a single vehicle into a chain stretched across space and time. He steps onto a deck of light and finds that photons can be turned into a lever if the architecture shifts from carrying power to receiving it. A sail that reflects light feels a push, because each photon reverses course and transfers twice its momentum. The push is small for any one photon, but the count of photons in a bright beam is vast, and an array of emitters that pours power into a tight column can press a thin film with steady force for as long as the beam stays locked. He begins with geometry because beams spread. Even a flawless source sees its light diverge according to wavelength and the size of the aperture. To keep a distant spot bright enough to matter, the emitter must be wide. Atmospheric shimmer will scramble the path so deeply, subrelativistic tests inside the solar system can start from mountaintops with adaptive optics, but a serious highway of beamed power demands emitters in orbit or on the moon to avoid the skies boiling. This demand transforms plan into infrastructure swarms of phase-locked lasers, or microwave dishes must tile sections of space like harbours, ready to hand off the beam as Earth turns and as the sail climbs a long line away from home. He studies the sail itself because a thin film is not simple. A perfect reflector would turn light without heating, but real materials absorb a fraction and warm. At high intensity, a film can ripple, tear, or balloon into buckling. Metals manage heat but weigh too much. Dielectric stacks of transparent materials can reflect strongly while handling temperature better, and they can be etched to shape the way the beam interacts with the sail, restoring stability when the center wanders. Diffractive patterns can in principle steer force toward the center if the sail strays, turning the beam into a restoring hand that keeps the craft balanced. Self-healing coatings that flow under micrometeoroid nicks can prevent rips from running, and meshes can bleed static charge to avoid arcing. Everything trades mass for resilience, and every gram saved on the sail can be spent on payload or on higher terminal speed. He considers stability, which decides whether a sail rides like a coin on a fountain or tumbles. A simple flat sail tends to be unstable, but a shallow cone redirects stray force toward the axis and acts like a dart. A curved rim can produce a gentle restoring torque. A light sail can also be spun to average wobbles, a compromise that adds gyroscopic calm but complicates the flip that braking may require later. In the beam, the sail must hold shape through gusts from the array, through small changes in reflectivity as it warms, and through tiny impacts from particles that arrive from ahead. He imagines a sail that speaks back to its beam with sensors that read pressure patterns and actuators that tweak tension to tune stability on the fly. Those systems must be simple and robust, because they must survive acceleration that could be measured in thousands of Gs for gram-scale probes, or in far gentler but extended pushes for kilogram and ton-class payloads. He turns to the margin on the sail edge where light leaks and damage begins. photon recycling's been proposed in which a second mirror sends light back to the sail for another push, multiplying thrust without increasing beam power, but it demands extraordinary alignment and adds optical elements that can fail. A simpler path is to accept limited efficiency in design so that when a tile fails, the damage stops at seams and the rest of the sail holds. Every choice shapes the maximum acceleration, the time spent under power, and the terminal velocity before the beam must give up, because at some range, even a mighty array cannot keep a distant sail bright. He follows the beam beyond the acceleration phase and asks how to stop. A sail that rides outward faces home and is pushed. To break at a destination, the sail must either turn and face a destination beam, which requires another vast array already waiting, or it must use fields and ambient plasma to shed speed, or it must surf a star's light and gravity in a photogravitational assist that steals pace by letting the star bend the path while the sail angles to push against motion. In the latter case, the sail must enter a stellar furnace and live through a blaze worse than the initial climb, and the geometry must be precise because a miscue at near light pace is a miss that wastes years. A magnetic sail can supplement photon braking by spreading a loop that pushes against the thin ionized wind around the target star. An electric sail that throws out charged tethers can do the same with electrostatic forces. Both replace reaction mass with patience and area, and both are vulnerable to dust and to the same blue shifted glare that earlier sections have warned about. He widens the architecture from a single sail to a chain. If arrays can hand off beams, then a craft can climb a ladder of light, gaining speed in relays and later shedding it in reverse. Such an interplanetary and then interstellar grid would be an enterprise measured in generations and in institutions as much as in watts. It would bind asteroids' moons and orbits into an economy, because a beam that can push a sail can also power a factory or a station that sits in shadow. He imagines microwave for early ladders because longer wavelengths are easier to phase across a vast array, and less troubled by dust on optics than a shift to shorter wavelengths for the final push where beam tightness matters. He considers pellets relatives of light in a staging scheme that throws mass instead of photons. A long-distance rail can fire a stream of tiny projectiles that the ship catches and throws to gain thrust without carrying them from home. The taut choreography here is brutal in its precision. The stream must arrive on time and on course, the catcher must swallow momentum without shattering, and the ship must ride the line without being sandblasted by its own feedstock. If the ship misses even a small fraction of the stream at high speed, the feed becomes a hailstorm. For braking, the stream can be arranged to meet the ship from ahead, or a magnetic sail can push against pellets that are ionized near capture, blurring the distinction between mass beaming and plasma braking. He visits governance because projects of this scale drag law and caution with them. A beam that can push a sail to a meaningful fraction of light speed is also a hazard if misused or mispointed. Safe corridors, cutoffs, and fail-safes are not decorations. A station that can power a beam must marry its optics to sky maps, to collision warnings, and to treaties that decide who aims and when. After the legal rails come the ethical ones. If sails become common, the sky will not remain pristine. The light of the arrays will leak and spill. Careful planning can minimize that spill using shutters, masks, and seasonal windows, and the craft themselves can be designed to drift dark once the push ends. He returns to physics and counts the gifts and penalties again. Beaming moves power off the ship and places it at home where mass and maintenance are cheap. Sails turn light into thrust without hot exhausts or turbine blades. The penalty is range alignment and the need for high reflectivity that holds across changing colour as the forward sky hardens from blue to ultraviolet. As the craft accelerates the spectrum of light in the ship, frame shifts and sail coatings that worked well at launch may absorb more at higher speed and heat more. Coatings that vary across the sail or that are tuned to a band of frequencies may help hold performance as conditions change. A sail that can feather to modulate its cross-section can manage heat and thrust, but every mechanism is a new point of failure. He ends this survey with staging in the larger sense. A near-light mission does not begin with the sail unfurling in darkness. It begins with years of building beaming stations and accuracy in tracking, with tests that drive small probes hard through the inner system to learn how films heal and how beams hand off, with deployments of braking fields around the target star that wait like harbours, and with protocols that guarantee that a narrow column of fury stays in its lane. Beams, sails and staging do not break the speed limit. They change how the approach looks, moving the burden to a network and turning the ship into a receiver. If that network grows, the line between mission and infrastructure blurs, and the goal begins to resemble not a single dash, but a road that others will use. That is the quiet promise in the lever of light, that once raised it can be set for the next traveller, and that the climb toward the ceiling will then be a series of steps, each one costly, each one exacting, but each one leaving behind a rung that endures. He walks into the brightest promise and finds teeth. Antimatter gleams because it converts mass to energy, with a thoroughness that chemical fire and nuclear fission cannot approach. When a particle meets its mirror opposite, their rest masses vanish into a spray of new particles and photons, and the accounting opens room for exhaust that races away at extraordinary speed. In the ledger that governs near-light travel, where every kilogram of propellant is a burden, and every unit of energy must be chased, this seems like the perfect currency. Yet as soon as he draws the engine on the board, the promise starts asking for collateral. Production is the first bill. On Earth, antimatter is created in accelerators when high-energy collisions throw a few rare antiparticles from a storm of ordinary fragments. Electromagnetic traps hold those antiparticles away from matter with magnetic and electric fields and cool them towards stillness. The capture rates are tiny by ordinary engineering standards, and each trapped particle required a cascade of energies to make and to isolate. Scaling to mission quantities means building factories that sit more like power plants than like laboratories feeding beams for years, harvesting with care and losing most of what they make to the inefficiencies of creation and capture. Space offers collection in principle, because planetary magnetospheres gather a mist of antiprotons from cosmic ray interactions with gas and fields, and a ring of scoops could in theory skim that mist. The densities are low, the collection surfaces need to be vast, and the harvest pace would be measured in patience rather than in buckets. The second bill is storage, and it arrives with an edge. Antimatter cannot touch ordinary matter without destroying itself and whatever it meets. Charged antiparticles can be suspended in electromagnetic bottles that use fields to confine them in a vacuum. Those bottles must be perfect for years, cannot afford a single speck of contamination, and must be wrapped in protection that defeats dust radiation and quench. Neutral antihydrogen trades the violence of charge for the slipperiness of neutrality. It can be trapped by magnetic gradients that catch its tiny magnetic moment, but the strength of that catch is weak, so the atoms must be very cold, and the fields must be large and well behaved. A starship that carries kilogram scales of antimatter must also carry a fortress of fields, structure cryogenics and control. Every layer adds mass, and the mass asks to be accelerated. The third bill is exhaust, which is where the dream becomes design. If antiparticles meet the hull dies. If they meet each other in open vacuum, their annihilation sprays energy in directions that do not favour thrust. In practice, an antimatter drive must either use the annihilation products directly as exhaust, or must thermalize the energy in a propellant that can be directed. A beamed core concept allows charged fragments born in annihilation to fly through a magnetic nozzle that bends them into a jet. This route tries to skip the penalty of heating heavy material and instead treats fast newborn particles as exhaust. It wins in principle on specific impulse because the jet carries pieces moving at a large fraction of light speed. It loses part of its energy at the moment of birth because a significant portion of the annihilation goes into neutral particles and photons that ignore the nozzle and blast the ship. Those neutral pions decay almost at once into gamma rays that flood the engine with penetrating light demanding heavy shielding that then eats away the gain. A solid core concept invites antimatter to annihilate within or against a dense propellant so that the energy becomes heat that drives that propellant through a conventional nozzle. This trades directionality in the birth products for directionality in the heated stream. It eases the radiation disaster but wastes some of the potential because heat cannot be moved into a rocket plume without losses, and the materials that receive the fury must survive temperatures that would ruin most solids. A gas core or liquid core variant tries to float the hottest region away from hard walls, but it still faces the old tyrannies of heat rejection and of erosion. He considers hybrids in which tiny packets of antimatter trigger microfusion in capsules that would not otherwise ignite, turning antimatter into a match that lights a denser tamer fuel. The triggered pulse can then be shaped by a magnetic mirror into thrust. This approach saves antimatter by leveraging its violence to kindle something that is easier to control in bulk. It adds a new choreography, a train of capsules, a feed system that never jams, and a containment that handles rapid pulses without shaking the ship apart. It inherits the truth that fusion products include neutrons and hard photons, and that these will ask for shields and radiators that weigh. He lets safety step from the wings, because an engine that depends on perfect containment invites the question of failure. A trap quenches and releases its charge. A micrometeoroid tears a thin wall and lets a handful of antiparticles kiss a support. A sensor undercounts a leak. Each of these is a small event that becomes a shower of energy in the wrong place. The design answer is brutal. Never carry a large store in one cage. Never place stores where a single strike can reach all wrap stores with surrogates that can swallow a burst and place the crew and the logic behind a permanent shadow shield that no operation ever removes. The control architecture must assume that it will be lied to by radiation, must vote its own data, and must refuse to allow any single hinge valve or coil to be a single point of loss. He turns to heat and sees the same loop that haunts every hot engine. Annihilation makes energy quickly, and the ship must move that energy along chosen paths. Magnetic nozzles must hold fields strong and clean in the middle of a particle squall. Structures that face a steady rain of gamma rays and charged fragments must heal or be replaced. But replacement at near light pace is a dream, so healing must be built into the material itself or must be avoided by geometry that places critical parts in permanent night. Radiators must again spread large and cold, and they must hide from the forward glare and from the engine's own flood of hard light. He adds biology to the picture and watches the margin shrink. Even a well-behaved antimatter drive will seed the ship with secondary radiation as birth products crash into structure. The crew will need to live in a vault of water and plastic deep in the mass, and passage through acceleration and deceleration phases may require them to retreat to shelters for days or weeks while the engine runs. Hibernation, if ever safe and reversible, would again be an ally more for shielding than for psychology, because small dense shelters are easier to protect. He lets governance enter, because antimatter blurs the line between engine and weapon. A store that propulsion treats as fuel is also a stockpile that a hostile act could turn against cities or stations. The same arrays and traps that build the fuel feed could in careless hands make a hazard. Any real program must grow inside frameworks that watch inventories, design fail-safes that make malicious release difficult, and place factories in orbits or on surfaces where accidental loss harms few. He returns to numbers not as citations but as a smell of scale. The energy release per unit mass of antimatter is so large that only a small supply could in principle push a modest probe very fast. But the mass of the cages, the field coils, the cryogenics, the shields, the nozzles, the radiators, and the attitude control needed to keep this orchestra playing can dwarf the fuel itself. When the aim is a heavy human craft, the supply must grow, and with it the scaffolding grows again. He offers a cautious speculation that points outward rather than inward. If antimatter is to move beyond laboratory trickle, its factories may have to live off Earth, where power can be beamed steadily from solar arrays that do not sleep, and where stupendous magnetic structures can be built without gravity. An inner system ring that feeds power to accelerator farms, and a cold outer system yard that assembles and tests storage modules could together turn a milligram decade into a gram decade progression. Even this does not touch the deepest barrier, which is not energy density but entropy management. Annihilation gives energy in fierce hard forms that want to go everywhere. A near-light ship must send most of that energy backward in an orderly way and must survive the rest. That design wrestles with geometry and heat more than with the romance of perfect fuel. He leaves this bright chamber with humility sharpened, not dulled. Antimatter is not a magic pass through the speed limit. It is an invitation to build fields that do not falter, traps that never touch nozzles, that turn chaos into a column, and homes for crews that never see the engine except as a distant hum through thick walls. It belongs in the family of near-light strategies as a keystone for small probes, and perhaps as a trigger for larger pulses. It does not erase the blue-shifted glare or the dust that turns to bullets, and it does not forgive errors in aim. The ceiling remains where it was. Antimatter simply offers a steeper stairway toward it, one that must be climbed with more care, not less. He walks into the gallery of geometry and finds engines that are not engines at all, only shapes of space-time drawn with careful mathematics. In this place, the craft does not plough through the medium itself flows. The simplest story is told with a bubble. Behind the ship, space swells. Ahead of the ship, space shrinks. The craft sits within a calm pocket where local speeds stay small, and laws remain unbroken while the edges of the pocket slide forward as if carried on a river that no propellant need stir. The concept is often called a warp metric after the first explicit solution that showed such a bubble could be drawn without tearing the equations of general relativity. He recalls the conditions that such a drawing demands. The energy that shapes a warp bubble is not the familiar positive energy that stars and planets contain. It is a strange bookkeeping entry that bends geometry in the opposite way to mass and pressure. Physicists call it negative energy density, and in classical matter it does not exist. Quantum fields, however, allow small regions in which energy can dip below the usual floor, as in the delicate forces that appear between closely spaced metal plates held in a vacuum. Those forces reveal that the quantum vacuum is not empty ledger paper, but a sea with fluctuations, and by cutting off some modes in a narrow cavity, one can create a region where the energy is lower than the surroundings. This is a hint, not a road. The hints come with strict rules known as quantum inequalities that limit how much negative energy can be gathered and how long it can be kept before the sea rebalances. The warp bubble that would carry even a modest craft appears to need not a whisper, but a shout of negative energy, distributed in a shell whose tension would tear ordinary matter and whose maintenance would demand control of fields beyond anything laboratories have approached. He follows the consequences with patience. A bubble that moves faster than light relative to distant stars creates horizons at its edges, boundaries beyond which signals cannot pass during the ride. Communication from the ship to the outside world would be blocked forward, and control signals from the outside to the bubble wall would be blocked backward. Steering would have to be arranged in the geometry itself before launch, or else the bubble would be blind and the ship inside would be a passenger of its own tide. Horizons also threaten particle creation that resembles the famous glow near black hole edges seeding the bubble boundary with radiation that could backwash into the pocket and warm the interior. Tidal forces at the sharpest gradients could shred structure, or at least demand reinforcement that would add to the same mass penalties faced by every other approach to speed. He tests a common comfort against the harsh details. It is true that the expansion of the early universe allowed distant regions to recede from one another faster than light without breaking causality, because the recession was not motion through space, but a stretching of space itself. The analogy tempts one to treat a local engineering of expansion and contraction as a natural extension of that cosmic behavior. The difference is arithmetic. The gentle expansion that continues today is measured in tiny fractions per billion years across each meter. The inflationary burst that smoothed the early universe occurred with an energy density that makes star cores seem cold, and it filled the whole cosmos at once. To mimic even a small patch of controlled expansion and contraction around a ship would require concentrations and signs of energy that local physics has never husbanded. The analogy is a map that shows a continent over the horizon, not a bridge that spans the ocean. He turns the bubble into a lens. Some modified designs reduce the energy demand by reshaping the shell, flattening it, or allowing only subluminal drift-lowering requirements while preserving a measure of the effect. These partial warps entice because they promise real, though modest benefits, reduction in apparent inertia, or a reshaping of field lines around a hull to soften drag from a medium or a means of bending a path around a hazard without changing the ship's local speed. In these softer renditions, the strange energy still appears, but the volume shrinks from astronomical to implausible rather than impossible. Even that shift is progress on paper, because it points research towards specific targets in material science and in field control rather than toward wishful generalities. He places wormholes beside warp bubbles because they share a need for forbidden accounting. A wormhole is a tunnel that connects distant regions of spacetime so that a traveller can step through in a time less than a signal moving through ordinary space would require. The mathematics permit such throats to be held open by negative energy threading their walls. As with the bubble, the quantum hints that such energy exists are accompanied by inequalities and instabilities that force the designs into regimes that are not known to be buildable. A wormhole that could fit even a modest probe would be a cathedral of geometry, and the scaffolding to keep it open would be a machine that burns against collapse for as long as anyone wishes to use the passage. He asks whether these visions break causality, and finds that even when the local rules are obeyed, global tricks can still cause trouble. Some bubble and wormhole configurations permit arrangements that evolve into loops in time where careful motion and manipulation lead to closed routes in which an event can lie in its own past. The conjecture that physics protects chronology declares that quantum effects rise up to choke such adventures but the proof remains a web of arguments rather than a sealed theorem. The prudent conclusion is that any scheme that toys with horizons and with topological shortcuts must be checked not only against energy budgets and metallurgy, but also against the oldest demand that effects do not outrun their causes. He lets the language of laboratories temper the grandeur. Experiments that measure vacuum forces across micron gaps that squeeze light in cavities to change the way it fluctuates, and that steer cold atoms through engineered potentials, all push in the direction of mastering fields with exquisite control. These do not build bubbles. They build confidence that the vacuum is a medium with structure that can be persuaded to behave in ways not obvious to 19th century intuition. Progress here would first manifest as sensors that beat thermal limits, as shields that suppress specific noise bands, and as tiny motors that surf vacuum gradients. Only after a long chain of such victories would the idea of distributing unusual energy across macroscopic regions even make sense as a question. He weighs what a warp conversation gives a near-light program even if the bubble never leaves the chalkboard. It trains engineers to think in terms of geometry, rather than only in terms of thrust. It motivates mapping the forward medium with precision, because a good map lets one pick paths through thinner gas and dust, which is a mundane cousin of bending space to ease passage. It legitimizes the search for metamaterials that can shape radiation fields, which can reduce dose and glare even if they do not tug on spacetime itself. It reminds everyone that horizons are not only astronomical but can be engineered by speed and by fields, and that planning for communication and control must respect surfaces beyond which information cannot pass during critical phases. He closes this chamber with a careful balance of wonder and discipline. Warp metrics and wormholes show that the equations of general relativity are permissive when taken as pure mathematics. They also show that when those equations are tied back to quantum fields and to materials that can be built, the permissiveness contracts to a narrow ledge. On that ledge stand ideas for modest field shaping, for partial reductions of effective drag for guidance systems that treat the forward gale as a fluid to be steered rather than only as a hail to be endured. The true light speed remains a limit, not because imagination is timid, but because the fabric that carries all motion has rules that bind local experiments to global order. If there is a future in which geometry becomes a tool, it will be born from long apprenticeships in laboratories that make negative energy less of a rumour and more of a measured resource, from astrophysical observations that reveal natural lenses and flows we can emulate, and from a culture of design that treats space-time not as a void, but as a medium with texture. Until then, the ship runs within the cone, pays the price for its pace, and uses geometry as a language for strategy, rather than as a lever to break the speed of light. He opens the smallest door and finds a landscape of rules that glow with promise, and then harden into walls. Quantum theory carries a rumour that the vacuum is not empty, and that entanglement ties distant things together in ways that ignore ordinary intuition. He tests each rumour against the need for motion. Entanglement seems to whisper of instant coordination, yet when two systems share a quantum state and then drift apart, no controllable message leaps between them when one is measured. The local statistics that any observer can read do not change until a slower-than-light comparison of notes is made. Quantum teleportation moves a state not matter or energy, and it requires a classical channel that cannot exceed the speed limit. The dream of sending steering commands or navigation updates across light years in no time dissolves into a discipline of encryption and correlation that is powerful but not fast. He asks the vacuum what it can give and hears a cautious answer. 0-point energy fills every mode of every field with a tiny hum that cannot be silenced without tearing the theory. but that hum cannot be harvested like fuel without paying the same energy back somewhere else. When two mirrors sit near one another, the modes between them change and a measurable force pulls them together. This force reveals structure, not bounty. It is a differential, a local reshaping of energy that has meaning only relative to a reference. Devices that try to surf that sea find that they are paddling in place, trading mechanical work for changes in field configuration that do not yield a net push-through vacuum. If a boundary is moved very quickly, real photons can be created from fluctuations in what is called the dynamic vacuum, but the energy in those photons comes from the motion of the boundary. The arithmetic refuses to allow a free lunch. He lets uncertainty enter because it is often offered as a loophole. The relation between position spread and momentum spread, and between energy spread and time spread, sets flaws under measurement precision and over how sharply a system can be prepared. Those flaws do not allow a craft to borrow energy without repayment in a way that leaves a lasting mark on motion. A ship cannot hop forward on a quantum credit card. What uncertainty does give is a map of what can be measured well enough to stay safe at speed. Hazard radars and star trackers face a noise that originates not in the electronics, but in the counting of photons and in the trembling of phases. Modern interferometers already squeeze fluctuations in one property to reduce noise in a chosen quadrature at the cost of increasing noise in its partner, and a near-light craft would lean on such squeeze light sources, quantum-limited amplifiers and single photon counters to see a dust lane before it blooms into a hail. Quantum practice, not quantum miracle, becomes a survival skill. He turns the lens on propulsion and sees quantum rules as bookkeepers of loss. Any engine that forces charges to dance in tight curves at high speed will shine hard photons and bleed energy. That radiation is a wall for exotic nozzles that try to herd charged fusion products or annihilation fragments into perfect jets. The very act of bending the stream drains it and warms the guides. Strong fields that promise to gather interstellar protons for a scooped engine run into pair creation at extreme intensities, where the vacuum answers too violently and makes electrons and positrons that feed turbulence and loss. Quantum electrodynamics does not forbid control, but it tallies every curve and every spike as a bill that heats structure and ruins coherence. He asks whether quantum tunneling, where a particle crosses a barrier it could not classically climb, might offer a path for signals or for thrust that outruns light. The answer is subtle in its mathematics and plain in its effect. In strange media, the peak of a wave packet can appear beyond a barrier at a pace that, if naively read, looks faster than light. Yet the front of any signal, the first non-zero nudge that carries information, never outruns the ceiling. The part that seems to hurry is not new information, but a reshaping of what was already on its way. In the same way, carefully prepared pulses in dispersive materials can be made to have group velocities that exceed the vacuum limit, or even become negative, but careful accounting always finds that no data step steps ahead of the light cone. The geometry that protected causality in earlier sections still rules here now, backed by experiments that have sought loopholes and found only clever illusions. He narrows to biology, which carries its own quantum rhetoric. The machinery inside cells runs on chemistry that at root relies on quantum bonds and on delicate energy landscapes. Some proposals imagine long-lived quantum coherence inside the warm fog of a living body coherence that might be useful for sensing or for protecting tissue from damage. At speed, the forward sky becomes a bath of hard photons and secondaries that smash states apart. Decoherence, the loss of subtle phase relations that quantum trickery requires to thrive, becomes relentless. A starship can carry qubits to process information, or to operate exotic sensors, but those units must live in vaults colder and cleaner than any crew space, and must be wrapped in layers of error correction that multiply the physical qubits required to hold a single logical bit stable. The price in power and mass rises quickly, and the correction codes must heal faster than radiation can wound. Quantum advantage for computation and sensing therefore becomes a rare tool deployed in special vaults, not a blanket that covers the ship. He brings temperature into focus because acceleration itself warms a horizon. A traveller that feels a steady push perceives the vacuum as a thermal bath, whose temperature rises with acceleration. This is a faint effect for ordinary rockets, and a debated one to measure, but its principle matters for extreme maneuvers. Attempting brutal accelerations to reach a target speed quickly invites a drizzle of perceived heat that grows with the push. Whether this plays a practical role in engineering depends on magnitudes that remain small until fantasies of millions of meters per second squared are drawn, yet the concept serves as a reminder that the vacuum is not a passive stage. Push hard enough, and it pushes back in new languages. He turns to communications again, not for speed, but for reach. Quantum states can be prepared that lie below the usual noise floor in chosen variables, letting receivers pick out weak signals from a background that includes starlight, the cosmic microwave background, and the glow of the ship's own bow shock. Coherent states, squeezed states, and entangled photon pairs can be used to beat naive classical limits on ranging and imaging. The improvement is real, but bounded. Losses in the path destroy delicate correlations detectors saturate, and pointing errors erase the advantage. The fastest channel remains light, and the best that quantum craft can do is to pack more certainty into each photon, and to waste fewer on noise. He asks the vacuum one more hard question. Can negative energy be tamed in small enough packets to become an engineer's tool rather than a theorist's object lesson? Quantum inequalities derived to keep the vacuum from being mined by clever cycles box in the amount and duration of negative energy that any arrangement of fields can achieve. A hallway of negative energy that could lower inertia or hold open a throat does not merely require a material that has not been found. It requires a choreography of fields that fight their own decay with finesse that dances at the edge of what a laboratory can even describe. Practical progress in that direction might first appear as tiny reductions in radiation, reaction, minuscule softening of drag in plasma flows around a hull, or local dimming of noise inside a sensor cavity. The grander goals remain over the horizon. He ends this survey where hope is strongest and honesty most necessary. Quantum theory enriches the toolkit. It makes better clocks that let navigation stay true when the forward sky narrows into a blue spear. It makes detectors that find a dust grain before it writes a bright line across a shield. It makes cryptography that keeps commands safe when relays bounce between worlds for decades. It allows simulations that capture materials at the level where a swift ion breaks a bond, and where a shield heals itself molecule by molecule. It does not grant dispensations from the limit that the constant speed sets. It turns the medium into a partner for measurement, not a highway for contraband signals. The walls it erects are as valuable as the windows it opens because they keep architects from wasting years on channels that will never carry load. The next turn brings the crew into the light, because human tissues, minds, and cultures have their own speeds and costs, and any plan that flirts with the large fraction of light speed must face that biology has frames of reference that do not stretch as willingly as clocks and rulers do. He brings bodies and minds into the cone of speed and finds that biology carries its own hard horizons. The ship that races at a large fraction of the speed of light will fold time for those inside so that months or a few years pass on board, while decades unfurl at home. Time dilation defined once and kept becomes a quiet solvent that works on family culture and memory even when every machine behaves. A traveller who leaves as a parent may return to meet great-grandchildren older than he is in his own accounting. Music, language and law grow strange while the crew counts only a handful of birthdays. Mission planners can write schedules that ignore nostalgia, but crew members live inside attachments and hopes that keep time in stubborn ways. He imagines a launch ceremony filmed from Earth and played in the cabin. In middle flight, the faces on that recording will already belong to a past that keeps receding, replaced by new recordings that must travel for years to catch the ship. The delay and drift do not forbid near-light flight. They turn it into a pledge to live with irreversibility. He shifts from calendars to cells and asks what a fast ship does to a body. Radiation has already been counted as a storm of photons and particles that splits bonds, shatters molecules and seeds, inflammation that does not always heal cleanly. The biology of repair is brave but limited, and a long journey at speed will accumulate lesions in tissues that divide quickly and in tissues that do not. Blood-making organs lose vigour. Lenses cloud and latent damage in the brain can steal clarity in ways that appear only slowly. Shielding of water and plastic storm shelters at the centre of mass and routines that limit exposure during bright passages may keep cumulative dose inside bounds that a life can endure, yet that margin is not generous. A crew that sleeps behind thick walls through acceleration burns, and through braking is a crew that must accept confinement and monotony in exchange for resilience. He watches gravity fade and remembers the lessons already learned in orbit. Without weight, fluids climb toward the head, eyes swell, and a fraction of flyers develop vision changes that ease only partly upon return. Bone and muscle grow spare unless they are taxed. The International Space Station taught that daily exercise can preserve strength and that specific loading patterns help bones keep their mineral, but even with discipline, some losses carry through. A near-light journey will require machines that pack a gymnasium's worth of force into a compact repairable system, because muscle tone is not a vanity, but a safety system for sudden maneuvers and for emergencies at arrival. Nutritional plans must carry enough protein and trace minerals to support constant rebuilding, and the closed ecology that feeds the crew must grow greens that refresh mood, as well as gut bacteria that support immune systems under stress. He brings circadian rhythm into the frame because sleep is not a minor variable. Human brains keep time with light and darkness, with routine, and with the right kinds of social cues. A fast ship will face a forward sky narrowed and brightened in a way that could bleed into the day if windows stare forward, and it will spend long stretches staring into the dim aft if windows stare back. The answer is architectural. Cabins must stage light carefully, mimicking dawn and dusk with colour and intensity that change on command, and common spaces must host seasons that keep time richer than simple cycles. When heat maps and dose maps force crew into shelters for days, the lighting and the soundscape must counter the compression. Dreams and mood become tools, not luxuries, and small rituals will keep the crew in a shared calendar when the universe outside no longer offers one. He asks whether hibernation can close the gap between biological time and mission time, and finds both hope and warning. Many mammals reduce temperature and slow metabolism for weeks without injury, and medical practice has learned to cool patients to protect the brain during delicate operations. Extending such rest to months or even years would cut radiation dose, ease the demands on food production, and turn monotony into a single long sleep. The risks are intimate. Muscles waste if they are not signalled blood clots in slow vessels. and the re-waking brain may not resume its old rhythms cleanly. Any attempt to hibernate crew will demand a scaffold of automated care that massages exercises and monitors without pause, and that can revive individuals safely if systems fail. The ethical knot tightens as well because consent given before a long sleep must be honoured by machines, while the person who gave it cannot revise it. He thinks about reproduction and development because generations will pass outside, while only a short arc of time passes inside. Carrying a child at speed means carrying fragile development inside a storm of secondaries that do not respect innocence. No one can guarantee that a womb paced by the ship's clocks will resist the rare but brutal strike of a single energetic ion. Sheltering works and statistics help, yet a cautious program will forbid conception, except inside heavy vaults, and will screen gametes and embryos with care beyond any current clinic. The same caution holds for microbiomes, the vast communities that share a body. Stress diet shifts radiation, and confinement can strip diversity and permit opportunists to bloom. The food forest inside the ship must be designed to feed not only calories but also a balanced ecology of microbes that teach immune cells to behave and that make molecules the brain requires to maintain even temper. He walks the halls of medicine and sees that autonomy is as vital as shielding. A ship that flees real-time support must bring imaging tools that fold, small, and deploy easily, must bring surgical spaces that can be cleaned in a storm, must bring libraries of tailored medications that remain potent after years in storage, and must bring robotic assistants that can hold hands steady or stitch in tight quarters. Training must cover more than procedures. It must teach crews to build and sterilize instruments from the materials at hand and to improvise when kits run low. The psychology of care matters because knowing that help will never come if a crisis grows large is its own slow toxin. Practices that tie crew to one another in trust that let conflict vent without taking root, and that sustain a collective story of why the journey matters, are as much part of survival as water and oxygen. He considers communication between ship and Earth under the twin weights of delay and drift. A message may take years to reach each way, and even if the crew ages slowly, the correspondence at home will age faster. Grief will arrive as files rather than as embraces. Mission control will change faces many times while a crew's roster stays steady. To keep the tie from thinning messages must be reframed not as conversation, but as letters, and the ship must cultivate its own culture and holidays that do not lean on Earth's calendar. Musicians aboard should make new music. Writers aboard should coin new phrases, and cooks aboard should shape flavors that are born from the ship's garden, so that the crew lives now rather than living in the reflection of a place that increasingly belongs to strangers. He turns to selection and justice because biology at speed can invite inequity if design is careless. People vary in how their bodies respond to radiation and to isolation. Some repair genetic damage briskly, some do not. Some thrive in close quarters, some grow brittle. A harsh program might be tempted to choose only the resilient and to discard the rest. A wiser program will design habitats and schedules so that a wider range of bodies and minds can thrive because a diverse crew is more robust to unknowns, and because exploration that preserves fairness is itself a kind of navigation through risk. He ends this passage with a pattern that echoes the engineering ledger. Near-light travel will not be denied by biology, but biology will tax every plan. Dose must be counted and avoided, muscles must be worked, sleep must be staged, food must be alive, care must be autonomous, culture must be grown on board, and the meaning of home must be allowed to change without breaking hearts. Years outside and days inside is not only a poetic line about clocks, It is a sentence that will be carried in bone, in mood, and in memory, and the ship that ignores it will fail, even if every engine sings. The next section will step from bodies to the machines that house them, because the craft itself must learn to endure and to decide when no hand can reach it, and that endurance will depend on autonomy, on shields that think, and on architectures that fail gently rather than catastrophically. He walks the corridors of a ship that must learn to think and to heal, because near light travel tears away the comforts of real-time help and leaves only what rides with the hull. Autonomy begins with the simple rule that no single failure shall be allowed to end the mission. That rule grows into an architecture of graceful degradation, where every function has siblings, where decisions are made by councils of machines instead of by solitary voices, and where the craft can continue to act with reduced performance, rather than tumbling into silence. The brain of such a ship is a distributed web of processors separated by real structure and by virtual fire breaks. These processors are built from devices that shrug off single energetic ions, and they store their memories in patterns that can detect and correct multiple errors. Every important calculation is performed at least 3 times by independent modules, and a majority vote decides the result. When a module begins to disagree with its peers too often, the network exiles it to quarantine and reimages it from a clean template, then asks it to rejoin the council. This is not paranoia. It is a common rhythm because the forward sky will endlessly flip bits, scramble states, and knock logic from certainty. The code that runs these councils is not clever for its own sake. It is boring by design, with functions that have been formally proven to behave within tight bounds, and with a recovery path that expects interruption by radiation. Where creativity is needed, as in navigation through a knotted dust field or diagnosis of an unmodeled vibration machine, learning tools are fenced within cages that report their confidence, and that must seek confirmation from conservative guardians before they touch actuators. The guardians would rather miss an opportunity to shave a day from arrival than accept a risk that could end the mission. He turns to sensing because a mind without clear eyes is a hindrance. The ship's face is a set of layered sensors that read the forward space with overlapping modes, radar for grains and clumps in the near field, LIDAR for shape and range when a body is near enough to scatter light, richly wide field cameras with filters tuned to catch the blue shifted glare without saturating, and particle counters that listen for the first rise in charged flux as a dust lane builds ahead. Each sensor has a partner that operates at a lower cadence and lower resolution, but with higher resilience, and each instrument can be folded behind additional shielding when the storm grows, leaving a more primitive scout to stand in the breach. The data from all eyes and ears are fused into a forward map that updates many times each second and that predicts the next many seconds in a rolling horizon. Autonomy lives there in those few seconds, because at the speeds that matter a small miss is disaster. When a grain the size of a seed threatens a vital radiator panel, the ship slews by a whisper, using control moment gyros and microthrusters to bias the shadow of the shield in the right direction. When the bow shock brightens, the magnetic fields swell and reshape, bending ions away from critical seams and tracing the plasma with lines that keep its heat from pooling in the wrong corners. He lets the shield itself become a machine that thinks. The forward bumper is layered with materials that change phase when struck, and heal micro cracks with heat that flows through embedded veins. Behind it lies a flexible lattice of ribs that can adapt their stiffness, bracing locally when a heavy hit is predicted and relaxing when the forward medium thins. Sprays of sacrificial dust launch from ports around the rim, to lay a mist ahead of the bow, not on schedule but on command from the forward sensors when they smell rise in risk. Magnetic coils around the nose carry currents that can be reshaped quickly to move the bow shock into cage-charged particles. These coils are cooled by loops that dump heat into radiators that sit in permanent night, and the control of those loops is tied to the same council of processors that fly the ship. If a coil begins to quench under a surge, the system redistributes current around it, accepting a hit in performance while preserving the integrity of the field. He watches maintenance unfold without hands. Behind the shield sit robotic arms that carry tools printers that can lay down metal and polymer, and stores of standardized tiles and vanes that match those embedded in the bumper. When a panel shows a pattern of fatigue when microphonics reveal loosened fasteners, or when a thermal image shows a hotspot, the maintenance swarm moves on rails and cables to effect repair. They work in pairs and trios, and they check each other as the brains do, because a single faulty torque could gouge a pressure line, and a single dropped tool at speed could become a projectile. The materials they feed are chosen for self-healing where possible. Polymers that flow under heat and then reset metals that carry microcapsules of flux that release when a crack opens, and composites, whose fibers can be re-anchored by local sintering, make the ship less dependent on perfect workmanship from machines that themselves will age. He weighs power and heat because autonomy must live on what it can carry and throw away. The power plant is a hybrid with a steady core that carries life support computation and the basic field geometry, and with pulsed sources that feed the drives and the magnetic shields during maneuvers. The steady core might be a compact reactor whose waste heat is bled into a layer of phase change materials before it is spread into the radiators so that short bursts do not create thermal shocks. The pulsed sources might be high-capacity capacitors and flywheels that seize energy during calm and release it when the ship must dodge or burn. Heat is the quiet tyrant again, and autonomy must act to prevent its accumulation long before any human would notice a dangerous trend. To that end, the ship runs digital twins of itself constantly with models that predict how heat and stress will move through structure given the next minutes of planned action and the last minutes of insults. If the twin predicts trouble, the plan changes and the crew hears about the change only after it has already been made and logged. He brings communication and culture of command into this architecture. A ship that can decide must also be able to explain. Every significant action is annotated, the confidence levels are recorded, the incoming data that drove the choice are preserved, and a compact narrative is forged and saved for transmission. These narratives will take years to reach home, but they teach the next ship. On board, the crew must trust that the vessel will never hide doubt. When the council hesitates, it says so, and a wake cycle can be interrupted to bring human judgment to bear. The line between the humans and the ship is not a master and servant divide. It is a partnership in which the creatures with bones and the creature with circuits keep one another honest. He adds a last layer one that uses the environment as a collaborator. Autonomy does not only mean thinking faster, it means designing so that the passive physics of the craft's shape carries it through common insults. Hull angles that naturally shed plasma away from seams, cable runs that cross only in armoured vaults, radiators that shatter into tiles rather than rip into sails, and shadows that multiply as structures unfold, all reduce the need for frantic correction. When the bow faces the gale, the fields and foams should settle into shapes that are stable under stress, rather than require constant attention. He ends the walk with a picture of a ship that is less a single object and more a colony that moves together. Councils of processors vote calmly under fire, shields sense and preact, Tools scurry and print, fields breathe and reshape, radiators hide and glow. Crew sleep and wake inside a culture that expects the vessel to carry out most of its duties without complaint, and that knows the vessel will call them when meaning ethics or new science are at stake. Machines learn to endure not by magic but by living inside rules that forgive mistakes and harvest small wins continuously. Only such a craft can ride the narrowed blue cone for years, survive the sandblasting of dust and the drizzle of hard light, and arrive with enough grace left to slow turn and begin work in a strange sky. He gathers the workable edges because the most honest path toward the ceiling is a braid of boundary cases that never trespass but come near enough for purpose. A first class of strategies accepts modest fractions of the speed of light and designs missions whose science and logistics still change the map. A probe running at 1/100th of the speed of light crosses a light year in a century slow by dream and fast by history. Such a craft could seed a lattice of sensors through the local interstellar cloud reading dust spectra, magnetic twists and the scale of turbulence at distances that telescopes cannot resolve. A string of these couriers each launched on a solar dive that ends in a deep Oberth maneuver, and a hot burn could build a weather report of the near-galactic neighborhood that future faster missions would treat as charts. At 1/10th of the speed of light, the possibilities widen. Flybys of nearby stars become missions that fit within a human career when measured by the clocks on board, and even the decades that pass at home can be made part of the plan if relays and successors are baked into architecture. To reach such pace with a payload measured in grams, a beam-driven sail can be pushed hard for minutes to hours. Accept a violent acceleration that no life could endure, and sprint toward a rendezvous that will be a skim and a flare rather than an orbit. The data can be compressed into narrow beams that fire backward along the wake, and a waiting net of receivers in the outer solar system can listen. For kilogram and ton classes, the edges look different. Solar thermal stages that drink heat on a near sun pass can add tens of kilometers per second to a trajectory. A compact fission or fusion stage fired while falling through perihelion multiplies that gain. The ship then coasts under fields and shadow. Breaking at the far end becomes the art and boundary cases turn enemies into tools. A magnetic sail can be spread until its wires see the thin ionized wind of the destination star and begin to push. An electric sail can charge long tethers and find drag in slow ions. If the ship carries no propellant for capture, it can aim not for the star itself but for a photogravitational assist that threads the glare and steals speed by letting the star bend the path, while the sail's angle turns light into a break. Each of these maneuvers lives under rules already drawn, the media are thin, the angles are unforgiving, and a small miss at high speed is not a detour, but a loss of the entire encounter. He studies navigation at the edge because guidance is where theory meets the silence between updates. At high fractions of the limit, aberration narrows the forward sky into a bright cone. Star trackers must learn catalogues that shift with speed, and their filters must move as the spectrum slides from blue to ultraviolet. Pulsar timing offers a fixed reference if the ship can keep its detectors cold and dark enough in a world that tries to warm and blind them. The ship's clock must remain true within tiny fractions of a microsecond over years, not as a luxury but because mistakes in timing become thousands of kilometers of miss. Communication stretches and tilts. Outbound signals are reddened for receivers at home. Inbound signals from home are blued in the ship frame, and the time between call and answer can be longer than an entire mission phase. A boundary case accepts this and treats command as doctrine that the ship revises on the fly, sending home narratives rather than pleas, and receiving new science rather than orders. He lets hazard management at speed become a strategy rather than a reaction. The forward dust cloud that earlier sections imagined as a sacrificial mist can be turned into an active bumper whose density is modulated according to the predicted flux, thickening through known dusty belts and thinning in clean lanes. Detached shields can ride a short distance ahead on tethers, absorbing the first blows and being reeled in for replacement by printed tiles when fatigue grows. Radiators are broken into many small panels that shatter rather than tear, so that a strike removes a tile and a fraction of capacity rather than unzipping a whole wing. The ship wears a skirt of charged tethers that flick away small charged grains, and that stir a thin plasma that changes how neutral grains break. These are not glamorous systems. They are the mundane crafts that make a sprint something more than a bet. He examines delivery at the destination because high speed changes what arrival means. A fast flyby can still work science if the instruments are ready to grab frames at ferocious cadence, and if the ship can seed orbiters while it flashes past. Tiny daughter craft that separate days or weeks before the encounter can curl into capture with their own microthrusters, while the parent sweeps by and becomes a beacon. If capture is required for the parent, the price is known. Mass must be carried to break, or fields must be deployed to push against the medium, or prior infrastructure must wait. A boundary case draws comfort from staging across time. One mission races ahead to lay a magnetic braking field in the outer reaches of the destination wind, powered by sails that sip momentum from the star. Another mission follows years later and slows against that preparation, entering as a guest rather than as a burglar. He lists edge tactics that look like cheats, but are not. A photon rocket that emits light as exhaust can in principle reach high fractions of the limit with perfect efficiency of mass use, but the power required is staggering, and the waste heat problem returns with new teeth. Because every watt that does not leave as collimated light must leave as thermal glow from radiators that cannot stare into the forward furnace. A neutral particle beam aimed from home can push a magnetic mirror on the ship, and add momentum without sails, avoiding some optical issues yet aiming a narrow stream across light years, compensating for tiny drifts and avoiding the disaster of misses that sandblast the hull, remain hard problems. A pellet stream that the ship catches to both accelerate and later brake by turning the stream into an incoming hail expands the range of beaming, but demands choreography at the edge of reason. These are boundary cases because they do not change rules, they change who pays. He pauses at ethics and consequence because near-light mistakes are not small. A gram of matter moving at 1/10 of the speed of light carries energy comparable to large conventional explosives. A kilogram would carve craters. A ton would be a weapon of extinction if it struck a world. Planetary protection therefore grows teeth for interstellar flight. Approaches must idle early trajectories that cross orbits of inhabited worlds must be forbidden, and any beaming infrastructure must carry shutters and masks that guarantee that no line of fire passes through a planet, a station, or a ship. The same care applies to communications. A beam that whispers across a light year must be kept inside lanes that do not blind unrelated experiments or harm biology. Boundary cases therefore include governance as part of design, because near-light travel without law is a hazard engine. He lets failure become an asset because rescue is unlikely. A ship that loses too many radiators or that suffers an engine wound must have plans to become a useful thing rather than a drifting tomb. It can turn into a long baseline radio relay into a beacon that times pulses for the next mission, into a platform that reads the medium for decades from a new angle, or into an intentional target that invites small probes to practice interception and repair. Designing for graceful retreat is not defeat. It is respect for a regime where margins are thin. He closes this survey with a picture of a road that is not a straight sprint but a staircase. Each step is a boundary case, a faster flyby that returns data never seen before, a beaming test that holds a fragile sail steady across millions of kilometers, a braking field planted years ahead by a quiet drone, a courier that hums in the night as a new lighthouse. None of these crosses the speed of light. All of these push against it in ways that matter. They mark a culture that treats the horizon not as a dare but as a contour to follow a line that keeps stories consistent, while still allowing ambition to press its face against the glass. The final turn will gather these strands and admit without surrender why the limit holds what paths remain open, and how the climb can continue without breaking the rule that lets the universe keep order. He gathers the trail of evidence and stands before the horizon again, seeing not a wall of denial but a contour that the universe has drawn to keep stories coherent. The speed of light in vacuum is not a preference of photons, it is the geometry by which space and time agree to keep accounts. Measurements from early eclipses of planetary moons to modern timing with optical lattice clocks say the same thing in many dialects. Rulers contract along motion clocks, slow as pace rises, and simultaneity is a local truce rather than a global decree. Particle rings flog protons with more and more energy, and gain almost no further speed trading input for mass energy and for deeper time dilation rather than for a breach in the ceiling. Gravitational waves shoulder past from colliding stars and arrive neck and neck with light to within tight bounds, making the constant a rule that even ripples in space-time respect. Nothing in these facts sneers at ambition. They say instead that ambition must choose its language. When engines throw momentum away, they heat themselves and light the vacuum with radiation that tallies every bend and every charge. When a ship leans into the thin medium between stars, dust that weighs less than a grain becomes a lance gas, becomes a furnace, and the forward sky narrows into a glare that turns comfort into calculus. When planners try to buy speed with beamed light optics, grow the size of cities, and must keep a column tight across distances that mock even perfect glass, when designers reach for antimatter traps and fields multiply until the fuel is the lightest part of the engine and the geometry of the nozzle decides how much of the violent birth of particles becomes thrust and how much becomes heat and hazard. Quantum hopes do not open secret roads. Entanglement coordinates outcomes without carrying controllable signals. The vacuum yields forces when constrained, but never free power to push against nothing. Negative energy flickers briefly as a quantum bookkeeping artifact that can be probed in narrow chambers, but will not yet paint a macroscopic shell that reshapes the path of a ship. Warp metrics and wormholes remain proofs that equations are generous, until materials and inequalities are invited to the table. Causality stands as the quiet sheriff behind every denial. Faster than light would let some observers watch an effect precede its cause, and the physics that preserves order therefore demands that local influence never outrun the cone that light defines. The guard is not merely philosophical. It is encoded in every beam that refuses to accelerate past the constant, and in every timing experiment that watches clocks diverge by precisely the predicted amount. Biology adds a human stamp to the same message. Bodies tolerate only so much radiation, crave cycles of light and dark, and need gravity's mimicry to keep bones and hearts stout. Minds carry calendars that drift painfully when years outside become days inside. Autonomy and architecture can shelter and assist, but they do not change the ledger. They learn to keep it. What can change sits in the middle ground. Materials can become quieter under ion strike and can heal rather than crack. Shields can learn to think, moving from inert plates to layered, responsive skins that shape plasma and flow sacrificial mist ahead of the bull. Radiators can hide and tile, and in exotic forms can even spray curtains of droplets that are recalled by fields trading vulnerability for area while staying in the ship's night. Clocks can approach perfection and let star trackers and pulsar beacons hold course when the forward sky tilts. Beams can phase and hand off, making a ladder of light that turns once only sprints into rehearsed corridors. Staging can migrate from a single vehicle to a choreography across years, so that one mission plants a braking field and the next arrives as if a harbour had been built in vacuum. Ethics can be embedded early, so that near-light momentum is never pointed across towns or worlds, just as shutters and treaties have been woven into the use of lasers and microwaves at smaller scales. Culture can adjust to letters instead of conversations, to crews that grow their own music and cuisine, and to the recognition that return is not a homecoming so much as a meeting with a cousin of home. The ceiling therefore holds while the climb changes shape. The way forward looks like a staircase of boundary cases that flirt with 1/10 of the speed of light for grams today, and for kilograms tomorrow that harvest tens of kilometers per second from dives near the sun, and add more with compact stages that test sails and beams over interplanetary ranges, that learn how dust breaks as speed rises, and that turn every failure into a stable platform rather than debris. It looks like a federation of tools that borrow push from light drag from plasma and timing from pulsars. It looks like a workforce that treats adaptive shielding digital twins and self-repair as normal, and that spends most of its money on power optics and radiators rather than on glossy hulls. It looks, in short, like a widening of the practical even as the fundamental refuses to move. He admits without surrender why the rule survives. If a rule knits laws across scales, if it keeps cause from being eaten by effect, if it emerges from equations tested in laboratories and in the sky, so often that their failure would bring down bridges as well as thought experiments, then a program that respects that rule will do more, not less. To chase a loophole that moves a message ahead of the cone is to starve machines and crews that could have reached real places under real physics. To accept the rule is to plan the long apprenticeship that makes the next rung possible. The open questions remain almost painfully compelling. Can compact fusion learn to pulse cleanly and to throw most of its charged products backward without eating its own throat? Can antimatter be manufactured at scales that serve probes without turning factories into hazards? And can its annihilation be tamed into orderly exhaust instead of diffuse fury? Can sails learn to carry not only gram-class payloads, but laboratories that weigh kilograms, and to break around other suns without waiting centuries for destination arrays? Can magnetic and electric sails be tuned to dance with real, knotted plasmas rather than with ideal flows, and can those dances be rehearsed in the outer solar system until surprises dwindle? Can quantum devices quietly lower noise in sensors and receivers enough that navigation and hazard mapping remain trustworthy when the forward glare hardens? Can crews live well inside cultures that are by design cut from their birth calendars and asked to grow new ones? None of these questions threatens the constant that began this journey. All of them trace a climb that is slower than romance but faster than resignation. He steps back from the horizon and names the shape he sees a limit that is a scaffold physics that is a partner rather than a jailer, and a future in which ships cross the dark, not by breaking the rule that keeps stories straight, but by learning every way the rule can be served while still carrying minds and instruments to places where today there is only starlight.